Hello, cowboys and cowgirls. This is Dr. Johnson. I'm one of the AP stats teachers at Capel High School, and welcome to this lesson on discrete random variables. What is a discrete variable? Well, it is a variable that takes on a countable number of values, usually the counts of things like soccer scores, test scores, number of children, number of chairs, number of tables, that kind of thing. Each value in a discrete variable has some probability associated with it. And as a reminder, a probability model is a mathematical representation of a random phenomenon, and it has three elements. It is defined by its events, sample space, and beliefs about the probabilities associated with each event. Let's do a very simple probability model. Suppose we flip a fair coin. I'm going to let my event H be that a heads comes up, my event T be that a tails comes up. So since I'm flipping just one coin, my sample space is simply HT. Those are all possible outcomes. But I also need beliefs about the probabilities. So voila, probability of heads is 1/2, the probability of tails is 1/2, and that's true because we're flipping a fair coin. Notice here that the probability of heads plus the probability of tails equals 1. We have to, our sample space has to cover all bases, so the sum of the probabilities must be 1. A random variable in this context is a variable whose possible values are numerical outcomes of a random process. So I want to just note here the difference in notation. If we use a capital letter for a random variable, that is referring to the variable itself, the weight of a selected student, the weight of a selected student. If we use a lowercase letter to represent a random variable, then we're referring to the value of a particular student, the ith student. Just as a reminder, we are going to be using the long run interpretation of probability. So the probability distribution of a random variable gives us all possible values and associated probabilities. The probability distribution tells us how often in a very long run a random variable takes each of its possible values. So here I have a slightly different probability distribution. Suppose I toss 3 coins. Okay, so my sample space is defined like this. One possible outcome is I could get all 3 heads. Another is that I could get 2 heads and 1 tails, and I've listed all 8 possibilities out here. Plus, you also have beliefs about the probabilities. That's a requirement for a probability distribution, and there I have it. And how did I get those probabilities? I just counted up the number of instances where I got 0 heads, or 3 heads, or 1 head, or 2 heads, and that became my probability distribution. That is a probability distribution. Note that the sum of the probabilities over all possible values must be 1. A cumulative probability distribution can be represented as a table or a function showing the probability of being less than or equal to each value of the random variable. So I haven't drawn a cumulative probability distribution here. I've just drawn the probability distribution, but the same principles would apply that you learned back in chapter 2 with regard to ogive charts. This is a graph of a probability distribution for the number of heads in 3 tosses. And we can use this kind of graph to determine what is the probability of getting 2 or more heads. Well, I just count up the probability of getting 2 plus the probability of getting 3. And there's several ways I can get 2, and only one way I can get 3 heads. The sum is 4/8 or 1/2. Expected value or mean. These are the same things. Expected value is the same as the mean. And how is it defined? Expected value or mean of a discrete random variable is the sum of the possible values weighted by the probability of each. Here's my formula. The mean is equal to the expected value. And then this is the formula right here. That's the formula for expected value. And that formula is on our formula sheet. It is, I take each x, multiply by its associated probability, and they add them up across all x's. And there's the formula for a function, expected value for a function. It is found by multiplying each possible value of the variable by its probability and then summing over all possible outcomes. This formula is on your formula sheet. You don't have to memorize it. You just have to apply it by substituting numbers from the problem into that equation. So here I've spelled it out in a little bit more detail. So the mean is equal to the expected value. And then that summation symbol, the summation of xi times its probability, I take x1 times its probability plus x2 times its probability. And then I put this little ... plus, that's to show that the series continues in a similar fashion all the way to the end. I have k possible outcomes, so it's xk times the probability of xk. So let's show you how this works in practice. Below is a distribution for the number of visits to a dentist in 1 year. So we have, with probability 1 out of 10, the persons do not visit the dentist during the year, and so forth. The expected value does not have to be a value that actually occurs, and never round expected values. So here's how I did my calculation. I take 0.1, I take 0 times this probability 0.1, plus 1 times this probability 0.3, plus 2 times this probability 0.4, and so forth. And then I add them all up. Now, when you do this, you don't have to show all of these things that you're adding. All you have to do is show the first two in the series and then write plus ... and your equal sign. Again, be sure to include units at the end and do not round expected values. The expected value does not need to be one of the values for x. How do we interpret expected value? Expected value is the average or mean value that we would obtain from an infinite number of observations. And here is my interpretation. If we were to randomly select many people, the average number of dental visits per year would be about 1.75 visits. 1.75 visits. Each of those underlined words is part of the grading rubric. You have to mention that we're using, you're taking many samples. And the average number of dental visits per year is about. It might be a little bit higher, might be a little bit lower, because remember, we're doing this in a long run and taking many samples, so it might vary a little bit. And here's a proof. You can go back to this later if you'd like. In this proof that I show that if the probability is the same for all outcomes, then the expected value is equal to x bar. Not a difficult proof, but you can pause here and look it over. I'm just going to continue. Variance. For discrete random variable x, the variance of x is defined as, and here I have the definition of variance. So again, it uses the expected value operator, and so what I'm going to do is I'm going to take each xi, subtract the difference from the mean, square that, multiply it by its probability, and do that for each xi, and then add them all up. And just the last sentence reminds you, standard deviation is the square root of the variance. So if I wanted to find the standard deviation, I just take the square root of the variance. So let's look at this and see how it works in practice. This is the same data I had before with the number of dentists, number of dental visits, and their probability. First thing I'm going to do, I'm going to break this down into just parts here, and I'm going to show you how to calculate the variance. The variance is that symbol, that formula right there. So I'm going to start by calculating the variance, and I'm going to do that for each observation x. So I take 0 visits minus the mean, I square that and multiply it by its probability. Then I turn to the the next color, the purple color, and I have one dental visit minus the mean. I square that, multiply it by its probability, and so forth. Then I add them all up, and I get 0.9875 visits squared. This is variance, so the units for variance is visits squared. Now to get standard deviation, I just have to take the square root of it. And the square root is 0.9937. Again, don't round these numbers. When to show your work on problems like this, what you have to do is to show I want you to show the first two terms that you're adding, and then you can do plus dot dot dot, and we understand where that we'll understand that you're going to follow the same. You'd follow the same pattern, and then you give your equal sign with the answer. Again, this formula for variance is on the formula sheet, but you have to show your work and include units. How do we interpret it? Standard deviation is the typical difference between the random variable and its mean. Here's the interpretation. If many, many people were selected at random, the number of each person's dental visits in a year will typically vary by about 0.9937 visits from the mean 1.75 visits. Each of those underlined words is critical to your answer and part of the grading rubric. You have to tell us that you're taking many, many people at random. Then you tell me that the number of the variable, the description of the variable, the number of each person's dental visits in a year will typically vary. That's the key words, typically vary by about, I want that word about in there because this is a long run probability. Visits, and what is it varying from? It is varying from the mean, and I give the value. So that is your interpretation of standard deviation. In this slide here, I have some information about continuous functions. For those of you in calculus, you might be interested to see how stats and calculus tie together. So you're welcome to look at this and this. So that ends our slide presentation for today. Thank you very much.